Mercury is the closest planet to the Sun, and one of the most difficult planets to actually reach. That should bother you. It took one spacecraft nearly 7 years to get there. Another one launched in 2018 and will not complete its arrival until late 2026. Meanwhile, missions to Jupiter, more than 5 times further from the Sun than Earth, have made the journey in 18 months. The rules of space travel are not the rules you would guess. Venus sits closer to Earth than any other planet. At its nearest approach, it is roughly 25 million miles away. And yet the engineers who designed Cassini, a mission to Saturn, used Venus as a waypoint twice on the way out. A spacecraft bound for a planet nearly 900 million miles away stopped at the closest planet first, swung around it, and kept going. That is not a detour. That is the only way it could be done. A spacecraft launched toward Neptune today would still be in transit when children born this year are finishing graduate school. 12 years is the fastest any mission has made that crossing. There is no shortcut. There is no faster road. The solar system is not arranged conveniently, and the physics of getting across it do not care what you would prefer. Here is the question at the center of all of this. If you tried to send missions to every planet, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all of them, one after another, how long would that actually take? Not in the abstract, not in a diagram where everything is labeled and the distances look manageable. In reality, with real spacecraft, real orbital mechanics, and real constraints on when you can launch and how long it takes to arrive, the answer is not comfortable. Mercury alone requires years of careful approach just to slow down enough to enter orbit. Mars requires waiting for an alignment that comes around roughly every 26 months. Saturn took Cassini nearly 7 years. Uranus has not been visited since 1986, and a mission launched today would not arrive until the late 2030s at the earliest. Neptune is even further. The numbers stack up in a way that stops feeling like astronomy and starts feeling like something else entirely. To send missions to all 8 planets, one after another, and account for the actual physics of getting there, you are talking about timelines that would outlast entire careers, entire generations, in some cases entire human lifetimes. The first thing to understand about getting anywhere in the solar system is that space travel has almost nothing to do with distance. This is not intuitive. When most people picture a mission to Mars, they imagine something like a long road trip. Point the spacecraft at the red dot in the sky, fire the engines, and drive until you arrive. The problem is that Mars is not sitting still. It is moving. Earth is moving. The Sun is pulling everything in curves. By the time a spacecraft launched toward Mars today would cross the gap between the 2 planets, Mars will have traveled hundreds of millions of miles from where it was at launch. If you aimed at where Mars is, you would arrive at empty space. Think of it like throwing a football. A good quarterback does not throw to where the receiver is standing. He throws to where the receiver is going to be. The receiver runs, the ball travels in an arc, and if the calculation is right, they meet at the same point at the same moment. Interplanetary navigation works on the same principle, except the receiver is a planet moving at tens of thousands of miles per hour. The ball is a spacecraft following a curved path through a gravitational field, and there is no second throw if the timing is wrong. The other thing to understand is that a spacecraft is not driving through space. It is falling through it. From the moment a rocket cuts its engines after launch, the spacecraft is essentially a projectile. It is not pushing against anything. It has no road beneath it. What it has is momentum from the launch and the gravitational pull of every massive object in the solar system, principally the Sun, constantly bending its path. Mission planners do not steer a spacecraft the way you steer a car. They calculate a trajectory, a curved path through the gravitational field that will intersect with where the target planet will be at a specific moment in the future. Then they launch at precisely the right time, on precisely the right heading, and let gravity do the rest. This is where Walter Hohmann comes in. In 1925, a German engineer named Walter Hohmann worked out the mathematics of the most fuel-efficient path between two planetary orbits. His solution was elegant and counterintuitive. The most efficient trajectory is not a straight line. It is a half ellipse. A spacecraft leaves Earth moving in the same direction Earth is already moving around the Sun, which adds Earth's orbital speed to the spacecraft's own speed essentially for free. That combined velocity carries the spacecraft out on a wide curving arc that stretches across space until the far end of the arc intersects the orbit of the target planet. At that moment, if the timing is right, the planet arrives at that same location. Spacecraft and planet meet. This path is called a Hohmann transfer orbit. It uses the minimum amount of fuel of any trajectory between two orbits, which is why nearly every interplanetary mission in history has followed some version of it. Fuel is the most constraining resource in spaceflight. Every kilogram of fuel you carry requires more fuel to lift it off the ground, which requires more fuel to lift that fuel, and so on in a compounding cycle that mission designers spend careers trying to minimize. The Hohmann transfer solves this problem by working with orbital mechanics rather than fighting them. But here is the part that breaks people's expectations. The Hohmann transfer is efficient, not fast. The arc a spacecraft follows to Mars takes roughly 260 days. The arc to Jupiter takes years, and the arc to Mercury, the planet closest to the Sun, is not necessarily short just because Mercury is nearby. How long the arc takes depends not only on the distance between the two planets, but on the difference in their orbital speeds, on the geometry at the moment of launch, and on what the spacecraft needs to accomplish when it arrives. A flyby requires one calculation. Entering orbit requires a completely different one. Orbital speed is the key variable that most people overlook. Every planet moves around the Sun at a speed set by its distance from it. Close planets move fast, distant planets move slowly. Earth moves at about 67,000 miles per hour. Mars moves at about 54,000. Jupiter crawls along at about 29,000. When a spacecraft leaves Earth for Mars, it starts with Earth's orbital speed and needs to bleed off some of that speed to fall inward toward the Sun's gravity. Except for Mars, which is outward, it needs to gain speed. For Mercury, which is inward and moving much faster than Earth, the problem is reversed and severe. The spacecraft has to shed an enormous amount of orbital energy to match Mercury's velocity. That process takes time and fuel in quantities that define the entire mission structure. Here is the other layer. The planets are not aligned in a way that makes every departure equivalent. The angle between Earth and the target planet at the moment of launch determines whether the Hohmann arc will intersect the target's orbit at the right moment. Too early or too late, and they miss each other. This means there are launch windows, specific periods when the geometry lines up correctly, that may only open once every year or two, or sometimes longer. Miss the window and you wait for the next one. The window for Mars, for instance, comes around roughly every 26 months. The window that allowed Voyager 2 to visit all 4 outer planets in sequence came around once every 175 years. This is the system that every mission is built inside. The distance between Earth and another planet is almost beside the point. What matters is where both planets will be at the moment of arrival, how fast they are moving relative to each other, how much energy is available to change the spacecraft's velocity, and whether the geometry at the moment of launch allows the arc to work at all. These factors together, not simple distance, determine whether a mission takes 7 months or 7 years. Every mission in history to every planet has been a negotiation with those same orbital mechanics, and the planets have never once agreed to make it easy. Mariner 10 launched in November of 1973, and it reached Mercury after a journey of 147 days. That number sounds almost reasonable, less than 5 months to the innermost planet. If you told someone that at a dinner table, they would probably nod and move on. This was because Mercury is the closest planet to the Sun. That means from Earth it sits sometimes as near as 77 million miles away at closest approach, closer than Mars, closer than Jupiter, closer than anywhere else in the outer solar system. 5 months to a destination that near does not sound unreasonable. Then you learn what Messenger required. Messenger launched in August of 2004. It did not reach Mercury until March of 2011. That is 6 years and 7 months of travel. Not because engineers made poor decisions or chose a slow route. That was the fastest viable path. Mercury sits closer to us than almost anything beyond Venus. It is one of the hardest destinations in the entire solar system to actually stop at. The reason has nothing to do with distance in any straightforward sense. It has everything to do with speed, with what the Sun's gravity does to anything that falls toward it. Here is the problem in its simplest form. When you fire a spacecraft toward the Sun, gravity accelerates it. The deeper into the Sun's gravitational well you fall, the faster you go. Mercury sits very deep in that well. Its orbital speed is roughly 107,000 miles per hour, nearly twice what Earth manages as it circles the Sun. A spacecraft arriving at Mercury after falling sunward from Earth is moving fast, far too fast for Mercury's gravity to hold. Mercury is a small planet. Its surface gravity is about 38% of Earth's. At typical interplanetary arrival speeds, a spacecraft simply flies past. The planet cannot capture it. To enter orbit, the spacecraft has to arrive moving slowly enough that Mercury's weak gravity can take hold. Slowing down while falling toward the Sun is not something that happens naturally or cheaply. The brute force solution would be to carry enough rocket fuel to fire massive engines in reverse upon arrival, killing velocity through sheer thrust. Engineers calculated what that would require for Mercury. The fuel mass needed would be so enormous that no practically buildable spacecraft could carry it to Mercury in the first place. The rocket equation punishes heavy spacecraft. The fuel required to slow down at Mercury adds weight that requires more fuel to launch. That adds more weight, which spirals into a vehicle too large to exist. So engineers solve the problem a different way. They take time instead of fuel, a lot of time. Gravity assists work in either direction. When a spacecraft passes a planet ahead of the planet's orbital motion, it gains speed from the planet's momentum. When it passes behind the planet's motion, relative to the Sun, it loses speed. That lost velocity goes into the planet in a technical sense, but the planet is so massive that the effect on it is completely immeasurable. For the spacecraft, the effect is significant. A carefully designed gravity assist flyby can bleed thousands of miles per hour from a spacecraft's solar orbital velocity without burning any propellant at all. The cost is trajectory complexity and time. Sometimes months of additional crews just to set up a single flyby at the right geometry. For Mercury, engineers need to line up many of these maneuvers in sequence, each one ratcheting the spacecraft's velocity slightly downward until arrival speed falls within the range Mercury's gravity can manage. Messenger's actual path through the solar system was one of the most intricate trajectories ever flown. After launching in August 2004, the spacecraft flew back past Earth in August 2005 in a gravity assist that reshaped its orbit around the Sun. It then moved toward Venus, swinging past in October 2006 and again in June 2007. 2 Venus flybys, each one pulling the trajectory slightly inward, slightly slower relative to Mercury's orbital frame. Then began the Mercury flybys themselves. January 2008, October 2008, September 2009. 3 separate passes of the actual destination, each one skimming close to the surface, each one shedding more orbital energy, each one making the spacecraft's path around the Sun more compatible with the orbit it needed to achieve. Finally, In March 2011, after 6.5 years, 1 Earth flyby, 2 Venus flybys, 3 Mercury flybys, MESSENGER fired its engines and let Mercury's gravity pull it into orbit. The science mission had not yet begun. The travel was only just finished. Mariner 10 had none of those constraints. It was not trying to stop. It executed a Venus flyby in February 1974 and then swung past Mercury for the first time in March of that year, photographing roughly 45% of the planet's surface over a few hours of close approach, because it was in a solar orbit that kept returning it to Mercury's neighborhood. It flew past twice more, September 1974 and March 1975, collecting additional images each time. What it never did was slow down. The spacecraft passed through Mercury's space at whatever speed it happened to be carrying. Mercury's gravity had no opportunity to hold it. A flyby mission has the physics working in its favor. There is no orbital insertion requirement, no need to shed thousands of miles per hour of velocity through carefully staged gravity braking that takes years to execute. You arrive, you pass, you observe for hours, and then you continue into space. The science is genuinely limited. Mariner 10 saw less than half the planet across all 3 passes, at distances that left enormous questions unanswered. But 147 days is fast. It is fast because the mission demanded nothing from Mercury except that it be present. This divide between a flyby and an orbiter is the fundamental split in planetary mission design. Mercury makes the difference more dramatic than almost anywhere else in the solar system. A flyby to Mercury requires a relatively modest trajectory. An orbiter requires a looping, doubling back, multi-year journey that uses 3 or 4 planets as stepping stones before the spacecraft is finally moving slowly enough to be claimed by Mercury's gravity. The years spent in transit are not wasted. Engineers take measurements throughout the cruise phase. The gravity assist flybys of Venus produce valuable science of their own. But the core reason for the detour is mechanical and unavoidable. MESSENGER spent 4 years in Mercury orbit after it arrived, mapping the planet completely, discovering that water ice exists in permanently shadowed craters near the poles, confirming that Mercury has a liquid iron core despite its small size, measuring a magnetic field that turns out to be substantially offset from the planet's center. None of that was possible from Mariner 10's 3 rapid passes. The years of travel purchased years of answers that could not have come any other way. Scale comparisons help make this concrete. If you shrunk the solar system to the size of a football field, Neptune would sit near one end zone and the Sun at the other. Earth would land somewhere around the 10-yard line. Mercury would be barely 4 yards from the Sun, practically standing on the goal line. On paper, on that diagram, it is within almost effortless reach. But getting there, stopping there, entering orbit around a planet sitting 4 yards from the goal, that demands a path that crosses half the field, loops back, swings wide, crosses again, before finally arriving at a destination that looks from a distance like it should have taken 20 minutes. Orbital mechanics does not care about apparent proximity. It cares about velocities and energy and the geometry of intersecting paths. For Mercury, every one of those factors works against the simplest route. BepiColombo is a joint mission of the European Space Agency and JAXA, the Japanese Space Agency. It carries 2 separate science orbiters stacked together during the cruise phase, equipped with instruments significantly more capable than anything MESSENGER carried. It launched in October 2018 on a trajectory that includes 1 Earth flyby, 2 Venus flybys, 6 Mercury flybys before final orbital insertion. Those 6 Mercury encounters are spread across years, each one reducing the spacecraft's velocity incrementally, edging it closer to the speed where Mercury can finally hold on. The mission's arrival timeline was pushed repeatedly as trajectory planners worked through the constraints. The final orbital insertion for both spacecraft is now scheduled for late 2026. BepiColombo, launched in 2018, will not complete its arrival at Mercury until late 2026. A journey of more than 8 years door to door to the planet that sits closest of all to our own Sun. Venus sits closer to Earth than any other planet, just over 25 million miles away at its nearest approach, and on paper it should be the simplest destination in the solar system. The numbers make it look easy. Mars at closest approach is roughly 35 million miles away. Mercury at its nearest is about 77 million miles. Venus beats both of them. For the earliest missions launched toward it, the travel time reflected that closeness in a way that almost nothing else in planetary exploration does. Mariner 2, launched in August of 1962, reached Venus in 109 days. The Soviet Venera probes averaged somewhere between 100 and 140 days in transit. These are short journeys by the standards of interplanetary space. 4 months to cross tens of millions of miles and arrive at another world. Compared to what Mercury demands, or what Saturn requires, Venus looks almost neighborly. But that framing misses something that turned out to matter enormously. Venus is not just a destination, it is the most useful gravitational tool in the solar system. The history of what humans have done with Venus has less to do with understanding Venus itself, and more to do with using it to reach everything else. To understand why, you have to understand how a gravity assist actually works, because the mechanics of it are not obvious. A spacecraft approaching a planet is falling into that planet's gravitational field. As it falls closer, it speeds up. As it swings around and climbs away, it slows back down. If nothing else were involved, the spacecraft would enter and exit with essentially the same speed relative to the planet, and the whole encounter would appear to accomplish nothing. But the planet is not sitting still. It is moving through space at its own orbital velocity, and the direction of the spacecraft's approach changes everything. If the spacecraft approaches from a specific geometry, the planet's motion adds to the spacecraft's motion. When the spacecraft exits the encounter, it is moving faster than when it entered, not relative to the planet, but relative to the Sun. The planet loses an infinitesimal fraction of its own orbital momentum. The spacecraft gains a meaningful fraction of speed. Nothing burns. No fuel is spent. The laws of physics do the work. For missions heading deep into the outer solar system, this matters more than almost any other single factor in trajectory design. Cassini used Venus twice. The spacecraft launched in October of 1997 and reached Venus for its first flyby in April of 1998, less than 6 months after leaving Earth. It came back around for a second Venus flyby in June of 1999, then Jupiter in December of 2000, and finally Saturn in July of 2004. Each of those encounters had to be executed with extraordinary precision, because the geometry required for one flyby to set up the next was calculated across years. Cassini did not go to Venus because scientists wanted data about Venus. It went to Venus because Venus was the only practical way to build up enough energy to reach Saturn with the rockets that existed in 1997. Galileo did something similar on its way to Jupiter. Launched in 1989, it swung past Venus in February of 1990, used Earth twice more in 1990 and 1992, and finally arrived at Jupiter in December of 1995. 6 years of travel, much of it spent looping through the inner solar system, picking up speed before climbing outward. The Parker Solar Probe takes this logic and runs it in the opposite direction, which is where things become genuinely strange. Parker launched in August of 2018, and its mission was to get as close to the Sun as any spacecraft had ever been. To do that, it needed to slow down relative to the Sun, to fall inward rather than orbit outward. Counterintuitively, you cannot simply point a spacecraft at the Sun and expect it to fall in. Earth is moving sideways at about 67,000 miles per hour in its orbit, and anything launched from Earth inherits that velocity. To get closer to the Sun, you have to shed that sideways speed. The way Parker's designers chose to do it was to use Venus, not to speed up, to slow down. Each Venus flyby adjusted Parker's orbit, gradually reducing its perihelion, the closest point of its path to the Sun, by a little more each time. The mission required 7 Venus flybys over the course of its primary mission, each one precisely timed, each one stealing a small portion of Parker's orbital momentum and depositing it into Venus's gravitational account. Parker reached its closest solar approach of 3.8 million miles from the Sun's surface in December of 2024, moving at 430,000 miles per hour. Venus made that possible, not through speed, but through subtraction. There is something worth pausing on here. Gravity assists are usually described as accelerating spacecraft, and most of the time they do, but the direction of the effect depends entirely on the geometry. A spacecraft approaching in front of a planet in the direction of its orbit gets pulled forward and gains speed. A spacecraft approaching from behind gets pulled backward and loses it. Parker needed the braking version. Most outer planet missions need the boosting version. The planet does not care which way the spacecraft approaches. It simply exerts gravity. The engineers decide what that gravity accomplishes. The Venera program, by contrast, went to Venus simply to study Venus. The Soviet missions dropped probes into the atmosphere, survived the crushing pressure and searing heat for brief periods. The surface temperature on Venus is around 900 degrees Fahrenheit, and returned data. Mariner 2 confirmed that the planet had no detectable magnetic field and surface conditions hostile to anything resembling life. These were fast missions with direct trajectories and straightforward objectives. They arrived quickly, accomplished what they could, and ended. They used Venus the way you would expect, as a place to go, not a lever to pull. Modern mission design has moved far beyond that framing. Venus now functions less like a destination and more like infrastructure. It sits at an orbital distance from the Sun that makes it extraordinarily useful for adjusting trajectories heading both inward and outward. The geometry works. The planet is massive enough to produce meaningful speed changes. It is close enough to Earth that spacecraft can reach it quickly before beginning the longer work of using its gravity. Every time a spacecraft swings around Venus, trading a fraction of the planet's orbital momentum for a change in trajectory, it is borrowing from a bank that has been remarkably generous to human space exploration. Mars is the most visited planet in the solar system, which says less about how easy it is to reach and more about how relentlessly humanity has tried. More than 50 missions have been aimed at Mars since the early 1960s. Rovers have driven across its surface. Landers have measured its wind. Orbiters have mapped its craters and canyons down to the width of a desk. By any measure, Mars is the most thoroughly pursued destination in the solar system beyond Earth. And yet, even with all of that accumulated effort, getting a spacecraft there remains a serious commitment of time. Not weeks, months, closer to a year, depending on when you leave and where the planets happen to be sitting. The average distance from Earth to Mars is roughly 140 million miles. But that number is almost meaningless on its own, because the distance between Earth and Mars is never fixed. Both planets are moving. Earth completes an orbit in 365 days. Mars takes 687 days. Their relative positions are constantly shifting, and the gap between them swings dramatically as a result. At closest approach, when the two planets line up on the same side of the Sun, Mars is only about 35 million miles away. At their furthest, when they sit on opposite sides of the Sun, the distance stretches out to nearly 250 million miles. That is a 7-to-1 swing in raw distance, depending purely on timing. A standard Hohmann transfer from Earth to Mars takes roughly 259 days, 8.5 months. The spacecraft does not travel in a straight line across that gap. It arcs along a curved path, following the geometry that was introduced in the previous section, aiming at where Mars is going to be rather than where it is when the mission launches. The result is a transit that consumes most of a year before the spacecraft ever reaches the planet. By the time Perseverance hit the Martian atmosphere on February 18, 2021, it had been travelling since July 30, 2020. That is a journey of just over 200 days, more than 6.5 months of coasting through empty space before the first contact with another world. Perseverance was not unusual in that regard. Mars Odyssey, launched in April of 2001, took about 200 days to reach orbit. Viking 1 and Viking 2, launched in the summer of 1975, each took roughly 11 months to complete their journeys. The travel times vary based on the specific launch window and the trajectory chosen, but the range is fairly consistent. Call it 6 months on the short end, 11 or 12 on the long end, with the majority of missions landing somewhere around 7 to 9 months in transit. There is no shortcut available within current propulsion technology. The physics of the Hohmann transfer defines the floor, and the floor is measured in months. What determines exactly how long any given mission takes is largely the question of when it leaves. Earth and Mars reach their most favourable alignment for a Hohmann transfer roughly once every 26 months. This is called the synodic period, the time it takes for the two planets to return to the same relative positions after one has lapped the other. During these windows, the geometry lines up in a way that makes the trip as short and fuel efficient as it is ever going to be. Outside those windows, the trajectory gets worse. The spacecraft has to travel farther, burn more fuel, or both. Mission planners are not choosing between a fast trip and a slow one. They are choosing between launching during the window or not launching at all. This creates an unusual rhythm to Mars exploration. Missions cluster around those 26-month windows. The 2020 window, which opened in midsummer, saw 3 separate missions launch. Perseverance from the United States, Hope from the United Arab Emirates, and Tianwen-1 from China. All 3 left within weeks of each other, because the window was open and all 3 mission teams understood what closing it meant. Miss the window, and the next opportunity is more than 2 years away. The science waits. The funding continues to flow. The engineers sit and watch the calendar. These extended delays between launch windows have shaped the entire cadence of Mars exploration, creating periods of intense activity, followed by years of relative quietude. A mission delayed beyond its window might not launch for another 2 years, meaning that careful planning and rigorous testing must be completed on a rigid schedule, or the entire effort is deferred indefinitely. Now consider what this means for a crewed mission. A human crew flying to Mars on a standard trajectory would spend roughly 8 months in transit. That is 8 months of exposure to cosmic radiation, 8 months of microgravity effects on bone density and muscle mass, 8 months of confinement in a spacecraft likely not much larger than a few rooms of an average house. They would arrive at Mars with bodies that have already taken a significant toll from the journey. Then comes the harder part. The crew cannot simply turn around and fly home. Earth and Mars will not be aligned for a return trajectory for well over a year after arrival. The planets have to travel far enough along their respective orbits to reach the next favourable configuration. That wait is typically around 14 to 16 months on the Martian surface. Not a brief visit, not a week of planting flags and collecting samples. More than a year of living on another planet in a pressurized habitat, dependent entirely on systems brought from Earth, before the window opens for the return flight. Then another 8 months to get home. The entire round trip runs to roughly 3 years. 3 years is the number that tends to land differently than the others. Not for a robotic spacecraft, which does not age and does not get sick and does not need to call its family. 3 years for people. 3 years away from Earth on a mission to a planet that, for most of history, was nothing more than a reddish point in the night sky. Mars is described as humanity's nearest realistic target for crewed exploration, and that framing is accurate. It is the nearest one, but nearest does not mean close. The engineering problem of getting humans to Mars is not primarily a vehicle problem or a life support problem or a landing problem, though it is all of those things too. At its foundation, the problem is time. The distances are so large that the transit itself becomes a mission, a months-long ordeal that has to be survived before any exploration can begin. Viking 1 took 11 months to reach a planet with no crew aboard, no need for food or water or breathable air, no biological clock counting the days. It was a machine, and 11 months was simply how long the trajectory required. A crewed mission would likely aim for a faster approach to reduce radiation exposure, but the physics of the Hohmann transfer imposes hard constraints. Trading efficiency for speed means burning more fuel, which means a heavier spacecraft, which means more fuel to lift that spacecraft out of Earth's gravity. The trade-offs compound quickly. The 26-month window is not a bureaucratic inconvenience. It is a gravitational fact. Earth and Mars are in motion, and they do not pause to accommodate schedules or budgets or political timelines. The window opens, the window closes, and the next one arrives on its own schedule regardless of whether humanity is ready. Every Mars mission ever launched, from Mariner 4 in 1964 to Perseverance in 2020, has had to negotiate with that constraint. All of them planned around it. None of them changed it. And if you miss the window, the planet simply will not cooperate. You wait 2 years and 2 months for the geometry to come back around, and then you try again. Past the asteroid belt, the solar system stops feeling like a neighborhood and starts feeling like something else entirely. The asteroid belt itself is not a dramatic physical barrier. Spacecraft pass through it without incident. There are no walls, no visible edges, no moment where an alarm sounds and the scenery changes. But the numbers on the other side of it are different in kind, not just in degree. Mercury sits roughly 77 million miles from Earth at its closest. Mars, at its nearest, is about 35 million miles away. Jupiter, at its closest approach, is nearly 365 million miles from Earth. That is not a longer version of the same journey. That is a different category of problem. Saturn is roughly 750 million miles away at closest approach. Uranus sits at around 1.6 billion miles. Neptune at nearly 2.7 billion. Each step outward is not a continuation of the pattern from the inner solar system. It is an escalation. There is a way to feel this that raw numbers do not quite capture. If you shrink the solar system down so that Earth and the Sun are 1 inch apart, Mars is about 1.5 inches from the Sun. Jupiter is more than 5 inches. Saturn is closer to 10. Neptune is over 30. The inner solar system, everything inside the asteroid belt, occupies the first 1.5 inches of that model. The outer solar system occupies the remaining 30. Most of the solar system, by any physical measure, is out there. This creates a problem that the Hohmann transfer orbit cannot fully solve. The Hohmann transfer is the most fuel-efficient path between 2 orbits, and it works well enough for the inner planets. For Mars, a Hohmann transfer takes roughly 259 days. That is a serious mission, but it is measurable in months. For Jupiter, a pure Hohmann transfer from Earth would take close to 3 years. For Saturn, over 6. For Neptune, the math returns a number close to 30 years. A 30-year Hohmann transfer to Neptune is theoretically optimal in terms of fuel, but it is completely useless in practice. No spacecraft lasts 30 years in transit. No mission budget or human patience accommodates it. Something else was needed. The deeper problem is that spacecraft lose speed as they climb outward from the Sun. This is not a flaw in the spacecraft. It is orbital mechanics. As a spacecraft moves away from the Sun's gravity pulls it back, and the spacecraft trades kinetic energy for potential energy, the same way a ball thrown upwards slows as it climbs. By the time a spacecraft crosses the asteroid belt and approaches Jupiter, it has bled off a significant fraction of the velocity it had when it left Earth. To keep going outward to Saturn, and then Uranus, and then Neptune, requires more energy than a single rocket burn can provide at launch. The energy has to come from somewhere else. The answer came from a graduate student named Michael Minovich, who in the early 1960s was working at JPL on trajectory calculations. Minovich worked out the mathematics of what happens when a spacecraft passes close to a planet in motion. If the geometry is right, the planet's gravity captures the spacecraft briefly, bends its path, and releases it moving faster than it arrived. The planet slows down by an amount too small to measure. The spacecraft speeds up by an amount that can mean the difference between reaching a destination and not reaching it at all. Minovich showed this was not just a theoretical curiosity, it was a practical tool. A few years later, Gary Flandreau extended the idea further. He was calculating trajectories for missions to the outer planets and noticed something about the orbital positions of the giant planets in the late 1970s. They would be arrayed in a configuration that occurred roughly once every 175 years. A spacecraft could fly to Jupiter, use Jupiter's gravity to gain speed toward Saturn, use Saturn's gravity to gain speed toward Uranus, and continue outward to Neptune. One launch, 4 planets, achieved through a chain of gravity assists that each added speed the rocket alone could never have provided. This was the gravity assist chain, and it transformed what was possible. The trade-off is real, though. Gravity assists are not free. To use a planet's gravity for a speed boost, the spacecraft has to be in the right place at exactly the right time, which means the trajectory is not a direct line. It curves, it loops, it sometimes requires flying toward Venus before heading toward Jupiter, or flying past Earth twice before departing for Saturn. These indirect paths add time and demand precision that compounds across years. If a spacecraft is slightly off course during a gravity assist flyby, the error does not just affect that leg of the journey. It propagates forward, growing larger with each subsequent planetary encounter. The teams managing these missions have to track trajectories with extraordinary care and issue course corrections years before the corrections are actually needed. What the gravity assist chain enabled, fundamentally, was a way to reach the outer solar system without building rockets that would otherwise have had to be enormous beyond any practical limit. The energy required to send a spacecraft from Earth to Neptune in any reasonable time frame, carried entirely by rocket propellant at launch, would have demanded a vehicle larger than anything ever constructed. There is no version of the outer solar system exploration story that does not run through Minovich and Flandreau and the mathematical framework they built in the 1960s. Without gravity assists, realistic missions to Jupiter would require launch vehicles so large they were beyond anything humanity had ever seriously considered building, and everything past Jupiter would simply be unreachable. Jupiter is bright enough to see without a telescope, steady and white in the night sky, the largest planet in the solar system, and it takes between 18 months and 6 years to reach it, depending on how you choose to go. That range is worth sitting with for a moment. 18 months, 6 years. Both numbers describe real missions to the same planet. The difference between them is not a matter of better technology or faster rockets. It is a matter of what the mission was designed to do, what energy was available, and how much time the engineers were willing to trade for fuel. Jupiter sits about 484 million miles from the Sun on average. From Earth, depending on where the two planets are in their orbits, the distance ranges from roughly 365 million miles at closest approach to more than 600 million miles when they are on opposite sides of the solar system. Those numbers are hard to feel in any visceral way. Here is one that might help. If you shrank the distance from Earth to the Moon down to a single inch, The distance from Earth to Jupiter would stretch nearly the length of a football field. The Moon, by that same scale, is sitting in your palm. Jupiter is somewhere near the far end zone, and yet it glows in the night sky bright enough to cast a faint shadow on the ground when conditions are right. The first spacecraft to reach Jupiter were the Pioneer probes. Pioneer 10 launched in March of 1972 and reached Jupiter in December of 1973, a journey of about 21 months. Pioneer 11 followed, arriving in December of 1974 after a similar transit. These were fast missions by the standards of what came after, built on relatively direct trajectories, carrying modest science payloads, and designed primarily to prove that a spacecraft could survive the asteroid belt crossing between Mars and Jupiter, which at the time was considered a genuine hazard. No one knew whether the density of material in the belt would destroy a spacecraft passing through it. Pioneer 10 answered that question and kept going. Then came Voyager. Voyager 1 launched in September of 1977 and reached Jupiter in March of 1979, a transit of about 18 months. Voyager 2 launched 2 weeks earlier, but followed a slower trajectory and arrived at Jupiter in July of 1979, roughly 23 months after launch. Both missions were fast by any later standard. They were designed for speed and trajectory efficiency above almost everything else, because the planetary alignment that made the Grand Tour possible demanded it. There was no room in the mission plan for long detours or extended gravity assist sequences. The window was open, and the spacecraft had to fly through it. Voyager 2's images of Jupiter's moon Io, volcanic and furious, arrived at Earth in 1979, less than 2 years after the spacecraft had left Cape Canaveral. Errol. Then something changed. The next mission to Jupiter was not a flyby. It was an orbiter. And an orbiter is a fundamentally different kind of commitment. Galileo launched in October of 1989. It did not reach Jupiter until December of 1995. 6 years and 2 months of travel time to a planet the Voyagers had reached in 18 months a decade earlier. The difference was almost entirely a matter of energy. Galileo was heavier than the Voyager spacecraft, carried more science instruments, and was designed to slow down enough to be captured by Jupiter's gravity and spend years in orbit rather than streaking past. Slowing down requires the same energy as speeding up, and Galileo did not have the launch vehicle to get there directly. Instead, mission planners gave it a different kind of engine, the gravity of other planets. Galileo's trajectory included a flyby of Venus in February of 1990, an Earth flyby in December of 1990, a second Earth flyby in December of 1992, and a pass through the asteroid belt that included a close look at the asteroid Gaspra in 1991 and Ida in 1993. Each of those encounters bent and accelerated the spacecraft, adding velocity that rockets alone could not have provided. The 2 Earth flybys are the strangest part of that list. Galileo flew away from Jupiter, came back around past Earth, and then flew toward Jupiter again, gaining speed from Earth's own orbital momentum in the process. It was an indirect path by any measure, but without it, Galileo never reaches Jupiter at all. What Galileo found when it arrived was worth the 6-year wait. The spacecraft spent nearly 8 years in Jupiter orbit, revealing the detailed structure of the planet's atmosphere, detecting an ocean of liquid water beneath the surface of Europa, mapping the volcanic activity on Io in unprecedented detail, and watching pieces of comet Shoemaker-Levy 9 slam into Jupiter's cloud tops in 1994 while still in transit. The science Galileo returned reshaped what planetary scientists understood about the outer solar system. All of that came from a spacecraft that needed 6 years just to get into position to start working. Now consider Jupiter's size. It is not just the largest planet in the solar system, it is larger than all the other planets combined. You could fit every other planet inside Jupiter and still have space remaining. Its Great Red Spot, a storm system that has been churning for at least 3 centuries, is wider than Earth. Its magnetic field is the largest structure in the solar system after the Sun itself, stretching in some directions nearly to Saturn's orbit. 4 of its moons are large enough that if they orbited the Sun rather than Jupiter, they would be classified as planets in their own right. Europa alone has become one of the most compelling targets in the search for life beyond Earth, carrying more liquid water under its ice shell than exists in all of Earth's oceans combined. Jupiter also functions as the solar system's most powerful gravitational tool. For any mission trying to reach Saturn, Uranus, Neptune or beyond, Jupiter's gravity is almost too useful to ignore. Voyager 2 gained 6 miles per second from its Jupiter flyby alone. 6 miles per second is not a small number. That is more than 21,000 miles per hour of velocity added to the spacecraft in a single encounter, with no propellant burned. To achieve the same velocity increase with a rocket, you would need an amount of fuel so large it would make the spacecraft practically impossible to launch. Jupiter's gravity did it for free, in exchange for a slight and infinitesimal change in the planet's own orbital momentum. This is why nearly every mission to the outer solar system either uses Jupiter as a waypoint or is carefully designed around the possibility of doing so. Cassini used Jupiter for a gravity assist on its way to Saturn. New Horizons used it on the way to Pluto. Voyager 2 used it on the way to Saturn and then onto Uranus and Neptune. Jupiter is not just a destination, it is the solar system's most important junction. Juno launched in August of 2011 and was built for a single purpose: studying Jupiter's interior structure, magnetic field, and atmospheric dynamics from orbit. It carried no instruments for studying other planets. It had no science objectives during the cruise phase. Its entire mission plan was oriented toward Jupiter and nothing else, and it still took nearly 5 years to get there. Juno used an Earth gravity assist in October of 2013, swinging back past its home planet 2 years into the mission to gain the speed it needed to cross the remaining distance to Jupiter. It entered Jupiter orbit on July 4, 2016. 5 years for a spacecraft carrying nothing but instruments pointed at its destination. No detours for science along the way. No extended observation campaigns at intermediate targets. Just the physics of getting from here to there, and the physics required 5 years. That is what Jupiter asks of any mission designed to stay. The flyby missions got there in 18 months to 2 years by sacrificing depth for speed, accepting a brief encounter in exchange for a faster arrival. The orbiters paid in time. Galileo paid 6 years. Juno paid 5. Both of them then spent years doing science that no flyby could have accomplished. The trade is real, and the trade has always been worth it, but it is never cheap. Juno launched in 2011 and did not slip into Jupiter orbit until July of 2016. 5 years of travelling across the solar system to reach a destination that on a clear night you can pick out with your eyes. When Cassini left Earth in October of 1997, the scientists who designed it would not see it reach Saturn for almost 7 years. That number deserves a moment. 7 years. A child born the week of Cassini's launch would be in 2nd grade by the time the spacecraft finally arrived at its destination. The researchers who spent their careers building the instruments aboard it, the radar, the spectrometers, the imaging systems, had time to publish other papers, attend their children's graduations, move between institutions, grow visibly older before the mission they had given years of their lives to finally started returning science from Saturn. This is what outer planet exploration actually looks like from the inside. Not a launch and an arrival, but a long, quiet wait, measured in years. Saturn sits roughly 886 million miles from Earth on average. The Sun is 93 million miles away. Saturn is nearly 10 times farther from the Sun than we are. That means that even at the speeds a spacecraft can sustain, reaching it is not a matter of months. It is a matter of years regardless of how you approach the problem. But the deeper issue for Cassini was not simply distance. The issue was energy. To launch a spacecraft directly to Saturn in 1997 and actually enter orbit around the planet rather than fly past it would have required a rocket so large it was not practically buildable. The fuel mass alone would have made the launch vehicle effectively impossible. There was no direct path that fell within the limits of what rocket technology could deliver, so the mission designers did something that sounds almost impossible when you first hear it. They sent Cassini the long way around. The route Cassini took to Saturn covered roughly 3.5 billion kilometers and required exactly 4 planetary flybys, each one precisely timed, each one extracting a specific amount of gravitational energy from a planet that had no idea it was being used as a slingshot. The first encounter came in April of 1998, about 6 months after launch, when Cassini swung past Venus. The geometry was arranged so that Venus's gravity bent the spacecraft's path and transferred a fraction of the planet's orbital momentum to the spacecraft, increasing its speed without burning a drop of fuel. Then Cassini continued outward, looped back, and flew past Venus again in June of 1999. 2 visits to the same planet, 14 months apart, each one pulling a little more energy from the planet's orbital motion. Venus didn't noticeably slow down. Cassini accelerated. The technique exploited a fundamental principle of orbital mechanics, that gravity acts the same on all objects regardless of their mass, but momentum transfer depends on the relative speeds involved. A small spacecraft moving past a massive planet gains speed while the planet loses an imperceptibly tiny fraction of its own orbital velocity. 2 months later, in August of 1999, Cassini did something that still feels strange to think about. It flew past Earth. A spacecraft that had been launched from Earth 2 years earlier came back around and used our own planet as a gravitational boost, skimming close enough to be tracked by ground observers before continuing outward toward Jupiter. The Earth flyby added another increment of speed. Then, in December of 2000, Cassini swung past Jupiter, the most powerful gravitational engine in the solar system, received the largest single velocity boost of the entire journey. Jupiter's gravity is immense. The flyby accelerated Cassini significantly and redirected it onto the final arc towards Saturn. From Jupiter, Cassini travelled for another 3.5 years before arriving at Saturn in July 2004. Each of those 4 planetary encounters had to be timed with a precision that is difficult to overstate. A deviation of a few seconds in the timing of a flyby, a trajectory error of a few kilometers at the moment of closest approach, would compound across the remaining years of the journey into an error large enough to miss Saturn entirely, or arrive at the wrong angle for orbital insertion. The navigation teams running these calculations were working with equations that had to hold true across billions of kilometers and years of elapsed time. When Cassini executed its Saturn orbit insertion burn on July 1st, 2004, crossing through a gap in the rings while firing its main engine to slow down enough to be captured by Saturn's gravity, the spacecraft was performing a maneuver that had been planned in precise detail years before anyone knew whether Cassini would even survive the interplanetary cruise. It survived. The burn worked. After 6 years and 9 months, the spacecraft was in orbit. The achievement was a triumph of navigation precision and engineering foresight, a complex maneuver executed flawlessly after years of travel through the vacuum of space. What followed was 13 years of discovery that changed what we knew about the outer solar system in ways nobody had fully anticipated. Saturn's rings, viewed from orbit rather than from Earth's distance, turned out to be structured in ways that existing models had not predicted. Thousands of individual ringlets, gaps, waves, braided features that reflected the gravitational influences of nearby moons. The rings were dynamic, not static. The level of detail Cassini returned redefined the basic science of planetary ring systems. These observations revealed that Saturn's rings were far more complex than mere collections of ice and rock. They were intricate systems shaped by gravitational interactions, collisions, and the presence of small moonlets embedded within them. The planet itself held surprises. At Saturn's north pole, the atmosphere organizes itself into a persistent hexagonal shape, a six-sided storm system, each side of which is longer than the diameter of Earth. The hexagon rotates with the planet. It has apparently been there for decades at minimum, possibly much longer. Nobody had predicted it. Nobody had a clean theoretical explanation for it when Cassini first confirmed its existence in detail. It became one of those discoveries that generates as many questions as it answers. Titan, Saturn's largest moon, had long been known to have an atmosphere. Cassini revealed what was actually inside that atmosphere. The Huygens probe, the European half of the mission, descended through Titan's orange haze in January 2005 and transmitted data from the surface for over an hour. What it found below the clouds was a world shaped by liquid methane the way Earth is shaped by water. Rivers of methane, lakes of liquid methane sitting in basins near the poles. Rain, erosion, a hydrological cycle running on a different chemical than any world humans had studied before. Titan turned out to be the only body in the solar system other than Earth with stable liquid on its surface. That liquid was not water. Enceladus was smaller and, before Cassini, relatively unremarkable on paper. Then Cassini flew close enough to detect something emerging from the moon's south pole. Geysers! Jets of water vapor and ice particles erupting from long fractures in the ice shell, called tiger stripes, spraying material into space. Cassini flew directly through those plumes and sampled them. The water contained organic molecules. Beneath Enceladus's frozen surface, there was a liquid ocean, kept warm by tidal heating from Saturn's gravity. That ocean was venting into space in real time. Enceladus immediately became one of the most scientifically significant objects in the solar system. Not because of its size or its orbit, but because of what Cassini found pouring out of it. None of that science was available until the spacecraft reached Saturn. And reaching Saturn required 6 years and 9 months of travel across 3.5 billion kilometers. 4 gravity assists from 3 different planets, a navigation precision that had to hold across the entire journey. A mission architecture built around the hard fact that no rocket available in 1997 could send a spacecraft directly to Saturn with enough fuel left over to slow down and enter orbit. The route Cassini took was not a compromise. It was the only viable option. Everything Cassini revealed about Saturn, its rings, its moons, the geysers of Enceladus, the methane lakes of Titan, came from a spacecraft that needed 6 years and 9 months and 4 planetary gravity assists just to get close enough to start seating data. Voyager 2 flew past Uranus in January of 1986, after a journey of 8.5 years from Cape Canaveral. That was the only visit. No probe has returned since. No orbiter has followed. No lander has been proposed that ever made it off a whiteboard and into a budget request that survived contact with reality. Of all the major planets in the solar system, Uranus is the one that humanity looked at once, briefly, from a moving spacecraft that never slowed down and then left behind entirely. The distance alone explains part of it. Uranus sits roughly 1.7 billion miles from Earth at its nearest approach. That is about twice the distance to Saturn, and Saturn already required Cassini nearly 7 years of travel time, with 4 planetary gravity assists along the way. Uranus is farther. The physics do not get more forgiving as you move outward, they get worse. Every additional billion miles requires more fuel, more time, more precise trajectory planning, and a longer commitment from everyone involved: the engineers, the scientists, the funding agencies, and the governments that write the checks. Voyager 2 reached Uranus after launching in August of 1977. It had already spent 4.5 years traveling to Jupiter, used Jupiter's gravity to accelerate towards Saturn, spent another 3.5 years reaching Saturn, and then used Saturn's gravity to redirect toward Uranus. By the time it arrived, it had been traveling for 8.5 years and was operating on software written nearly a decade earlier. The flyby itself lasted only a matter of hours. Voyager 2 was moving too fast to stop, too committed to its trajectory to linger. It had Neptune waiting on the other side. But in those hours, it found things nobody expected. The magnetic field was wrong, not slightly off, profoundly structurally wrong. On Earth, on Jupiter, on Saturn, the magnetic poles sit roughly near the rotational poles, tilted maybe a little, but recognizably aligned with the axis the planet spins on. Uranus had a magnetic field tilted nearly 60 degrees away from its rotational axis, and offset from the planet's center by a significant fraction of the planet's radius. The field was lopsided. It wobbled as the planet rotated. Nobody had predicted that, and nobody has fully explained it since. Then there was the orientation of the planet itself. Uranus does not spin upright like the other planets. It rolls. Its rotational axis is tilted roughly 98 degrees from vertical, which means it orbits the Sun essentially on its side. Its poles face the Sun directly at certain points in its 84-year orbit, leaving one hemisphere in continuous daylight for decades and the other in continuous darkness. The seasons on Uranus are 42 years long on each side. During Voyager 2's flyby, the South Pole was pointed almost directly at the Sun, which meant the spacecraft was approaching a planet that looked, from one angle, like a pale blue-green target, almost featureless. The extreme tilt made interpreting what was even being observed a strange exercise. Voyager 2 also found rings. They were faint, narrow and dark. Not the brilliant architecture of Saturn's rings, but something quieter, harder to see. It counted 10 known moons during the flyby and discovered 10 more. The moons themselves were odd. Miranda, one of the smallest, had canyon systems so deep and terrain so fractured that some researchers initially suspected a catastrophic collision had broken it apart and reassembled it. The other moons showed evidence of complex geological histories crammed into bodies too small, by conventional thinking, to have generated the internal heat required to produce them. All of that came from a few hours of data collected by a spacecraft that did not stop, gathered nearly 40 years ago, with instruments designed in the early 1970s. That is the entirety of what humanity knows about Uranus from direct observation. Everything else is inference, telescope observation from Earth and from orbit, models built on incomplete information. The reason no follow-up mission has launched is not indifference. The planetary science community has ranked a Uranus orbiter among its highest priorities for decades. The 2011 Planetary Science Decadal Survey listed it as a flagship mission concept. The 2023 Decadal Survey went further and named a Uranus orbiter and probe its top priority for the next large-scale planetary mission. The scientific case is not in dispute. Uranus and Neptune represent a category of planet, ice giants, that appears to be extremely common in planetary systems detected around other stars. We have almost no understanding of how they work from the inside because we have never spent significant time near one. The obstacle is time, not political will, not scientific consensus, not even cost alone. Time. A mission designed to enter orbit around Uranus using current propulsion technology, and whatever gravity assist sequence the trajectory allows, takes somewhere between 13 and 15 years from launch to arrival. That number does not compress easily. The flight path to Uranus typically requires a Jupiter gravity assist, which constrains the launch window. Miss the window and you wait. Use the wrong trajectory and the spacecraft either does not have enough energy to reach Uranus at all, or arrives moving too fast to be captured into orbit. Getting into orbit around Uranus, rather than flying past it the way Voyager 2 did, requires arriving slowly enough for the planet's gravity to hold on. That demands either a very long, carefully planned trajectory or a propulsion system capable of significant braking burns at arrival. And braking burns require fuel, and fuel adds mass, and mass has consequences for everything else about the mission design. A mission funded and approved in the next few years would launch sometime in the late 2020s or early 2030s, depending on the trajectory options available. From there, the spacecraft travels. Engineers grow older. Scientists who wrote the original instrument proposals move into different stages of their careers. Graduate students who joined the team during the proposal phase finish their PhDs, complete postdoctoral fellowships, get faculty positions, and advise their own students before the spacecraft ever enters Uranus orbit. The mission is a commitment that spans professional lifetimes. What would an orbiter find? The magnetic field alone is enough to justify the mission. Understanding why it is so tilted, whether the geometry reflects something unusual about Uranus's internal structure, whether the interior is fundamentally different from Saturn and Jupiter, whether the ice and water and ammonia believed to exist in its deep interior behave in ways that explain the strange field. None of that can be answered from Earth. The rings, the moons, the atmospheric chemistry, the question of what actually drives Uranus's weather in a planet that seems to radiate almost no internal heat, all of it remains open. The earliest any realistic Uranus orbiter mission could arrive is the mid-2040s, which means a generation of planetary scientists is spending entire careers waiting for the data from a single mission to a single planet. Neptune is almost 2.8 billion miles from Earth at its closest approach, a number that is genuinely difficult to make feel real. Uranus already stretched the imagination. Neptune makes Uranus look close. If you drove a car at highway speed without stopping, without sleeping, without ever slowing down, you would arrive at Neptune in roughly 5,000 years. The number stops meaning anything almost immediately. What it actually means, in practical terms, is that reaching Neptune requires a level of patience and precision that no other planet demands quite so severely. And yet humanity has been there, once. Voyager 2 is the only spacecraft in history to have visited Neptune. Not one mission since has come close. No orbiter, no flyby, no probe. Neptune has been seen up close exactly once, during a window of days in August of 1989, and everything we know about it in any real detail traces back to that single encounter. The spacecraft that made it possible launched on September 5, 1977, 12 years before it arrived. The engineers who designed it had to aim at a target that would not be in position for more than a decade. They had to calculate where Neptune would be in August of 1989 before the Voyager program had completed its first planetary flyby. The math had to be essentially perfect from the start. The journey itself was a chain. Voyager 2 did not travel to Neptune in any direct sense. It traveled to Jupiter first, arriving in July of 1979. Jupiter's gravity bent its path and accelerated it significantly, redirecting the spacecraft towards Saturn. Saturn arrival came in August of 1981. Another gravity assist, another course change, another boost in speed. From Saturn, Voyager 2 curved outward toward Uranus, arriving in January of 1986. Each planetary encounter was not just a scientific opportunity, it was a necessary mechanical step. Without Jupiter's gravity, the spacecraft could not have built enough speed to reach Saturn in any reasonable time frame. Without Saturn, Uranus, Without Uranus, Neptune, the planets themselves were the engine. The rocket that launched Voyager 2 provided the initial push, but it was the solar system's own architecture, 4 gravity assists strung across 12 years, that actually carried the spacecraft to the edge of the planetary system. By the time Voyager 2 reached Neptune, it had been traveling for 4,388 days. The people who had designed and built it were 12 years older. Some had moved on to other projects. Some had retired. The spacecraft itself had crossed more than 4.4 billion miles of space and was arriving at a planet that had never been seen from anywhere closer than Earth's best telescopes. No one knew exactly what was there. What they found was strange. Neptune, at first glance, looks like the kind of planet that should be relatively calm. It is an ice giant, cold and distant, receiving roughly 900 times less sunlight than Earth does. There is no obvious reason to expect violent weather, and yet Neptune has the fastest recorded winds of any planet in the solar system. Wind speeds measured during the Voyager 2 flyby exceeded 1,200 miles per hour. The planet is driven by some internal heat source, radiating more energy outward than it receives from the sun, and that energy translates into atmospheric violence on a scale that has no equivalent anywhere in the inner solar system. The most visible feature Voyager 2 captured was the Great Dark Spot, a storm system embedded in Neptune's southern hemisphere, roughly the size of Earth, rotating counterclockwise with a period of about 16 days. The structure resembled Jupiter's Great Red Spot in basic form, a persistent oval vortex carved out of the planet's upper atmosphere. The difference was that when the Hubble Space Telescope looked for it in 1994, the Great Dark Spot was gone. A new dark spot had appeared in the northern hemisphere instead. Neptune's storms are not permanent fixtures. They form, they dominate the atmosphere for years, and then they dissipate. Whatever dynamics govern the planet's weather operate on timescales that have so far been impossible to study properly, because studying them requires a spacecraft in the vicinity of Neptune for more than a few days. Triton was the other discovery that changed how scientists thought about the outer solar system. Neptune's largest moon is roughly 1,680 miles in diameter, smaller than Earth's moon, and it orbits Neptune in the wrong direction. Every other large moon in the solar system orbits in the same rotational direction as its parent planet. Triton goes backwards. This retrograde orbit is not something that forms naturally from a disk of material coalescing around a young planet. It is the signature of a captured object, something that originated elsewhere and was pulled into Neptune's gravitational grip. The leading explanation is that Triton was once a Kuiper Belt object, a body from the vast reservoir of icy debris that lies beyond Neptune's orbit, captured billions of years ago through a gravitational interaction that has never been fully reconstructed. A moon that used to be its own world. The implications reach far. If Triton is captured, it tells you something about how chaotic the early outer solar system was, and how objects that formed in one region ended up in completely different ones. Triton also has geysers. Voyager 2 photographed dark streaks on the surface rising from vents, plumes of nitrogen gas and dark material shooting several miles up into the thin atmosphere before being carried downwind. A moon at the outer edge of the planetary system, where sunlight is almost absent, where surface temperatures fall to -391 degrees Fahrenheit, is geologically active. The energy that drives those geysers is not well understood. Triton's orbit is slowly decaying. In roughly 3.6 billion years, tidal forces will break it apart, and Neptune will gain a ring system comparable to Saturn's. All of this from a flyby that lasted a matter of days. The communication challenge during that flyby was its own kind of problem. Light takes approximately 4 hours to travel from Neptune to Earth. A radio signal sent from ground controllers to Voyager 2 during the Neptune encounter took 4 hours to arrive. The spacecraft's response, whatever data it was transmitting back, took another 4 hours to cross the same distance in the other direction. Every instruction had an 8-hour round-trip delay built in. If something had gone wrong during the flyby, any corrective command sent from Earth would have arrived long after the critical moment had passed. The entire sequence had to be pre-programmed, autonomous, and trusted completely. The team on Earth watched the data come back, not in real time, but in deep delay, receiving confirmation of things that had already happened 4 hours earlier. No mission has been sent to Neptune since. The reasons are not mysterious. Any spacecraft designed to enter orbit around Neptune rather than simply fly past it faces a transit time of 12 to 15 years using current propulsion technology and any realistic gravity assist sequence. A mission approved and funded today, with favourable launch windows, would not arrive until the late 2030s at the earliest, and more likely the early 2040s. The mission planning is complicated further by the fact that Neptune's position in its orbit shifts the available gravity assist geometry. The alignments that made Voyager 2's trajectory possible were specific to the 1970s. Different geometry means different routes, different transit times, different fuel requirements. A Neptune orbiter proposal has circulated through planetary science priority surveys for years. It has never made it to final approval and funding. What that means scientifically is difficult to overstate. Neptune is a major planet. It is a world with violent weather, a captured moon, active geysers, and a magnetic field tilted 47 degrees from its rotational axis in a way that no current model fully explains. Scientists know all of this from a single flyby conducted 35 years ago with instruments that were designed in the 1970s. The resolution of the best Voyager 2 images of Neptune's surface features is roughly equivalent to what a backyard telescope can resolve for Mars. Entire categories of questions about Neptune and Triton remain open, not because the science is too difficult, but because the spacecraft is not there. Voyager 2 is still out there, past Neptune, past Pluto, moving through interstellar space, and the signal it sends back now takes more than 18 hours to reach us at the speed of light. New Horizons launched on January 19, 2006, carrying the fastest initial velocity of any deep space mission NASA had ever launched, and it still took 9.5 years to reach Pluto. That number deserves a moment. 9.5 years. The spacecraft left Earth moving at over 36,000 miles per hour relative to the planet, faster off the launch pad than anything NASA had ever sent into deep space. It crossed the orbit of the Moon in 9 hours. 9 hours compared to the 3 days it took Apollo. And still, by the time it finally arrived at Pluto in the summer of 2015, the engineers who built it had aged nearly a decade. Some had retired. Children had been born after launch and started high school before the mission reached its target. The distance is the reason. Pluto sits, on average, roughly 3 billion miles from Earth. That number is technically accurate and practically useless. 3 billion miles is not a number the human brain can hold. What the brain can hold is this. If you drove a car at highway speed without stopping, it would take you roughly 6,000 years to get there. New Horizons, the fastest thing of its kind, needed 9.5. The spacecraft did not travel alone exactly. It had help. In February of 2007, about 13 months after launch, New Horizons swung past Jupiter. The flyby was not incidental, it was essential. Jupiter's gravity grabbed the spacecraft and flung it forward, adding roughly 9,000 miles per hour to its already extraordinary speed. That single encounter shaved years off the journey. Without the Jupiter gravity assist, New Horizons would have needed at least 3 additional years to reach Pluto, arriving in 2018 rather than 2015. The mission designers knew this before launch. The Jupiter flyby was built into the plan from the beginning, timed to the month, with the spacecraft's trajectory calculated to extract the maximum possible energy from the encounter. After Jupiter, New Horizons entered what the mission team called the cruise phase. For long stretches of that cruise, the spacecraft was placed into electronic hibernation. Not all of it, all at once. The team maintained basic systems and checked in periodically, but the instruments were powered down, the processors slowed, and the spacecraft essentially slept its way across the outer solar system. This was not laziness. It was engineering discipline. Every hour a system runs in deep space is an hour of wear it will never get back, and the mission needed those systems functional and precise when they finally mattered. 9 years later, during a flyby that would last less than a single day. The approach phase began in January 2015, 6 months before the flyby. At that point, Pluto was still just a smudge in New Horizons cameras, brighter than it had been, but unresolved. Over the following months, the image sharpened. Features appeared. A bright region in the southern hemisphere became visible weeks before arrival. Nobody knew what it was yet. July 14th, 2015. The flyby. New Horizons passed within 7,800 miles of Pluto's surface, which in interplanetary terms is extremely close. The closest approach happened at about 7:49 in the morning, Eastern Time. The spacecraft was not listening to anyone from Earth at that moment. It couldn't be. Signals from New Horizons at that distance take about 4.5 hours to reach Earth, traveling at the speed of light. A command sent from Mission Control would take 4.5 hours to arrive. Any response from the spacecraft would take another 4.5 hours to come back. That is a 9-hour round trip for a single instruction. If something had gone wrong during the flyby, the spacecraft would have been on its own. There was no possibility of intervention. The entire flyby sequence was pre-programmed. Every instrument activation, every image, every measurement, all of it scripted weeks in advance and uploaded to the spacecraft's memory. The team on Earth had done everything they could do. Then they let go and waited. New Horizons flew past Pluto autonomously, alone, 3 billion miles away, following instructions written by people who would not know if those instructions had worked until the data started arriving hours later. What the spacecraft sent back was extraordinary. Tombaugh Regio, named for Clyde Tombaugh, who discovered Pluto in 1930, turned out to be a vast heart-shaped plain of nitrogen ice, roughly the size of Texas and Oklahoma combined. It is one of the most recognizable features in the solar system now, immediately iconic, though no human eye had ever seen it before July of 2015. Surrounding it were mountain ranges made of water ice, some peaks rising more than 11,000 feet above the surrounding plains, comparable to the Rocky Mountains. These were not expected. Pluto is small and cold and was assumed to be geologically dead, frozen in whatever state it had settled into billions of years ago. The mountains suggested something more active, a world still processing heat, still changing. The atmosphere surprised everyone as well. Pluto has a thin envelope of nitrogen, and when New Horizons looked back at the planet from the far side, it photographed that atmosphere backlit by the sun. What it found was a faint blue haze, the same scattering of light that makes Earth's sky blue, produced here by a completely different chemistry at the edge of the solar system. The colour was unmistakable. Charon, Pluto's largest moon, had a red polar cap. The origin of that cap is still debated. The leading explanation involves methane escaping from Pluto's atmosphere, drifting to Charon, freezing at the pole, and then being chemically altered by ultraviolet radiation into reddish compounds called tholins over millions of years. Even the moon has a story that no one had predicted. After the flyby, New Horizons did not stop. It could not stop. There was no mechanism to slow it down, and no reason to. It continued outward into the Kuiper Belt, the vast ring of frozen objects beyond Neptune. In January 2019, it flew past a small contact binary object called Arrokoth, two lobes of ancient material barely 22 miles across, joined at a narrow neck. It was the most distant object a spacecraft had ever closely examined. Arrokoth turned out to be pristine, undisturbed by collisions or heating for essentially the entire history of the solar system, a relic from the formation of the planets themselves. New Horizons is still operating. It is still moving outward at roughly 36,000 miles per hour, sending back data from regions of the solar system no probe has ever reached. Its power supply is slowly fading. By the 2040s, the spacecraft will likely fall silent. At that point, it will be so far from Earth that its signals, traveling at the speed of light, will need nearly a full day to make the crossing. The mission that began with a launch in 2006 and reached its target in 2015 will have spent decades in the dark, still transmitting, still moving, long after the last of its designers have grown old. New Horizons is still out there, still transmitting, and by the time it finally falls silent sometime in the 2040s, its signals will take nearly a full day to cross the distance back to Earth. In the mid-1960s, a young scientist named Gary Flandreau at NASA's Jet Propulsion Laboratory noticed something in routine trajectory calculations that would eventually become one of the most important discoveries in the history of space exploration. Flandreau was working on a fairly routine assignment, identifying potential trajectories for future deep space missions, when the numbers revealed something unusual. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would drift into a rough alignment that happens only once every 175 years. Not a perfect straight line, nothing so clean as that, but close enough that a spacecraft launched at precisely the right moment could use each planet's gravity as a slingshot toward the next, hopping from giant to giant across the outer solar system in a single continuous journey. Without that alignment, reaching Neptune from Earth required a direct shot across billions of miles, carrying enough fuel to slow down at the far end. No rocket that existed, or that could realistically be built, was capable of that. With the alignment, the planets themselves became the engine. Flandreau ran the numbers carefully. The window opened in 1977. It would stay open for only a few years. After that, it would close, and nothing would reopen it for more than a century and a half. The concept that emerged from those calculations had an appropriately grand name: the Grand Tour. NASA's initial vision was ambitious. A fleet of spacecraft would launch in sequence, visiting all 4 outer planets, dropping probes, conducting extended observations, documenting worlds that no human instrument had ever seen up close. Preliminary designs called for specialized spacecraft designed around the mission's scale. The projected costs were significant. Then the budget reality arrived. The early 1970s were not generous years for NASA. Apollo had wound down. Political appetite for large-scale space spending had cooled. The original Grand Tour concept, as designed, was cancelled. The spacecraft were too expensive. The mission was too elaborate. What survived was a stripped-down version. 2 spacecraft instead of 4. Simpler in design, cheaper to build, carrying a reduced but still scientifically formidable set of instruments. They were called Voyager 1 and Voyager 2. Voyager 2 launched first, on August 20th, 1977. Voyager 1 launched 16 days later, on September 5th, 1977, on a faster trajectory that would allow it to arrive at Jupiter first, despite leaving Earth second. The twin spacecraft were remarkably similar in design, yet each carried distinct scientific instruments tailored to their specific missions. Both were equipped to study atmospheric composition, magnetic fields, and particle radiation in unprecedented detail. The decision to build 2 spacecraft instead of the original multi-spacecraft fleet provided a critical operational advantage. If one encountered catastrophic failure, the entire mission would not be lost. The engineering team designed both Voyagers to operate with complete autonomy for extended periods, a necessity given the growing communication delays as they travelled outward. Each spacecraft carried a golden record with sounds, images, and greetings from Earth in 55 different languages, a message from humanity intended for any intelligence that might someday find it in the depths of interstellar space. The practical meaning of that alignment is worth sitting with for a moment. Voyager 2's journey to Neptune took 12 years. It covered roughly 4.4 billion miles. At every planetary encounter along the way, the spacecraft arrived moving faster than it had at the previous one, having borrowed speed from a planet's orbital momentum. Jupiter added roughly 6 miles per second to Voyager 2's velocity relative to the Sun. That single encounter compressed what would otherwise have been additional decades of travel time into something manageable. Without Jupiter, there was no Saturn flyby on any reasonable timeline. Without Saturn, there was no Uranus. Without Uranus, Neptune was simply unreachable. The whole mission was a chain, and every link depended on the one before it. The alignment was not a convenience. It was the mission's entire structural foundation. Voyager 1 reached Jupiter in March of 1979, roughly 18 months after launch. What it found there was staggering. Active volcanoes on Io, the detailed structure of the Jovian cloud bands, the thin ring system around Jupiter that nobody had confirmed was there. Then Voyager 1 continued to Saturn, arriving in November of 1980. It threaded through the ring system, made close passes of several moons, and transmitted imagery that scientists were still analyzing years later. At Saturn, Voyager 1's mission to the outer planets ended. Mission planners had made a deliberate choice. Instead of continuing toward Uranus and Neptune, Voyager 1 would be directed into a close flyby of Titan, Saturn's largest moon. Titan had an atmosphere. That made it scientifically irresistible. But the geometry required for a close Titan approach flung Voyager 1 upward, out of the plane of the solar system entirely, on a trajectory that made Uranus and Neptune impossible. Voyager 1 traded the rest of the Grand Tour for a better look at one moon. Voyager 2 was not given that constraint. It continued on its ordained path, reaching Saturn in August of 1981, Uranus in January of 1986, and Neptune in August of 1989. 12 years after leaving Earth, the spacecraft arrived at the edge of the known solar system and revealed Neptune in detail for the first time. A storm the size of Earth churned in the planet's southern hemisphere. Triton, Neptune's largest moon, erupted with geysers of nitrogen ice. The encounter lasted only a few hours. Then Voyager 2 continued past Neptune, past Pluto, into the region beyond the planets. Voyager 1, moving faster and on a steeper outward trajectory, crossed into interstellar space in 2012. The announcement came after years of careful analysis. Scientists were debating precisely where the boundary between the Sun's influence and interstellar space actually fell, and the data from Voyager 1 was their primary instrument for finding it. The spacecraft detected a sharp change in the density and direction of the particles surrounding it, consistent with leaving the heliosphere and entering the interstellar medium. It was the first human-made object to do so. As of now, Voyager 1 sits roughly 24 billion miles from Earth. The signal it sends back, traveling at the speed of light, takes more than 22 hours to arrive. It is the most distant object humanity has ever built, and it is still out there, still transmitting, still returning data about the environment beyond the solar system. Voyager 2 crossed into interstellar space in 2018, roughly 6 years after its twin. Both spacecraft run on radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. Those generators have been slowly losing power for nearly 50 years. NASA periodically shuts down instruments and heaters to conserve energy and extend the missions. Engineers have estimated that meaningful scientific data may continue returning into the early 2030s. After that, the generators will no longer produce enough electricity to power the transmitters, and contact will be lost. The spacecraft will continue moving outward into interstellar space, carrying their golden records and their instruments in permanent silence, still drifting at roughly 35,000 miles per hour. Unreachable and unretrievable. What is remarkable about this is not just what the Voyager missions accomplished, but what made them possible. An alignment of planets that occurs once every 175 years, identified by one scientist doing routine calculations, exploited within a precise window measured in months. If Flandreau had made his discovery 10 years later, it would already have been too late. If the launch had slipped by a few years for budget reasons, the window would have closed. The outer planets would have scattered back into their usual uncooperative positions, and everything from Uranus onward would have remained unexplored, possibly for another century. The missions did not just require technology and funding and political will, they required the planets to cooperate, which they do only on their own terms and our own schedule. No mission has returned to Uranus or Neptune since Voyager 2 flew past them. The travel times required using any currently operational propulsion system are measured in more than a decade each way, and no such mission has been funded. The data humanity has on both planets still comes primarily from those brief flybys in 1986 and 1989. The window that made Voyager possible, the planetary alignment that occurs roughly once every 175 years, closed in the early 1980s, and the next one will not open until approximately 2153. On December 24, 2024, the Parker Solar Probe reached 430,000 miles per hour, the fastest any human-made object has ever traveled. That number deserves a moment. At that speed, you could circle the entire Earth in under 4 minutes. You could cross the continental United States in roughly 20 seconds. It is a velocity so far beyond anything in ordinary human experience that comparisons almost stop working. And yet, even at 430,000 miles per hour, the solar system barely flinches. At that speed, reaching Mars at average distance would still take around 4 months. Jupiter would be nearly 2 years away. Neptune, the outermost planet, would require close to 15 years of travel. The number that broke every speed record in history is still not fast enough to make the outer solar system feel close. This is the part that should genuinely disturb anyone who thinks carefully about it. The distances involved are not just large, they are large in a way that exposes the limits of speed itself as a solution. There is something important to understand about how the Parker Solar Probe reached that velocity. It did not achieve 430,000 miles per hour by firing its engines harder than any spacecraft before it. It achieved that speed by falling. The probe executed a close pass around the Sun on December 24th, dropping to within about 3.8 million miles of the solar surface. And as it fell toward that closest point, the Sun's gravity accelerated it the same way gravity accelerates anything falling toward a massive object. The probe was essentially in free fall at an extreme depth inside the Sun's gravitational well. When it swung back out, it was moving at record speed, but that speed was temporary. As it climbed away from the Sun, gravity bled the speed back off again. The Parker Solar Probe is not a fast spacecraft in any sustained sense. It is a spacecraft that gets briefly, extraordinarily fast at one specific point in its orbit, and then slows back down. This distinction matters enormously. The speed that makes headlines is not the speed that would get a spacecraft to Neptune. For long interplanetary journeys, what matters is sustained velocity maintained across hundreds of millions or billions of miles. And the record holders for that are not the Parker Solar Probe. They are the Voyager spacecraft and New Horizons. Voyager 1 has been traveling for nearly 50 years and is moving at roughly 38,000 miles per hour. New Horizons crossed the distance to Pluto at around 36,000 miles per hour, sustained over 9.5 years. For comparison, the Apollo astronauts made their journey to the Moon at about 25,000 miles per hour. So the genuine sustained speed record for deep space cruise is sitting somewhere in the range of 35,000 to 40,000 mph per hour, a number that is remarkable by any terrestrial standard and still produces travel times measured in decades for the outer planets. What would Parker's peak speed actually change? If a spacecraft could somehow maintain it across an entire interplanetary journey? The math is instructive. Voyager 2 reached Neptune in 12 years, traveling at roughly 35,000 miles per hour. A spacecraft holding 430,000 miles per hour continuously would cover the same distance in just over a year. That is a genuine, dramatic improvement. But it requires something that does not exist. A propulsion system capable of maintaining that level of thrust not for a few seconds, not for a single orbital pass, but for years. Chemical rockets burn for minutes. The speeds they produce are fixed at engine cutoff. After that, a spacecraft coasts. It does not accelerate. It simply carries whatever velocity it was given at launch and gradually loses some of it climbing out of the sun's gravity well. This is the ceiling. The problem with reaching the outer solar system faster is not that engineers haven't thought about speed. It is that no propulsion system currently in operational use can push a spacecraft continuously for the years that would be required to make a meaningful difference in transit time to Neptune or Uranus. You can build a faster rocket, and that gives you a somewhat faster coast. Voyager was faster than Pioneer, and Pioneer was faster than the spacecraft before it. Each generation gained something, but each generation was still coasting, and coasting across 3 billion miles takes a long time, no matter how fast you start. There is a related problem on the deceleration side. Getting to Neptune quickly means arriving at Neptune quickly, which means arriving with enormous velocity. A spacecraft traveling at sustained high speed and carrying no way to slow down will simply fly through the Neptune system and keep going. Every mission that has entered orbit around a planet, Galileo at Jupiter, Cassini at Saturn, Juno, Messenger, had to slow down on arrival. Slowing down requires fuel, or an atmosphere to brake against, or both. Neptune has no solid surface and only a thin upper atmosphere. Slowing an incoming spacecraft enough to achieve orbit requires either a massive fuel load or years of gentle deceleration, neither of which pairs well with the goal of getting there faster. So the honest accounting looks like this. The fastest object humanity has ever built hit 430,000 miles per hour for a brief period while falling around the sun. Sustained, practical interplanetary cruise speeds for the best missions ever flown have been closer to 35,000 to 40,000 miles per hour. At those speeds, Neptune takes 12 years. At Parker's peak speed, Neptune would still take somewhere in the range of 13 to 15 years by most practical calculations that account for the sun's gravity slowing a spacecraft as it travels outward. The improvement is real, but not transformative. The fastest thing we have ever built would still take more than a decade to reach Neptune, and that is the most honest summary of where interplanetary travel currently stands. Every travel time in this conversation is built on the same foundation: chemical rockets, the same basic propulsion technology that humanity has been using since the first ballistic missiles of the 1940s. A chemical rocket burns fuel, expands gas, and pushes itself forward by throwing mass backward. That is the entire principle. It has not changed in 80 years. And for reaching orbit, for escaping Earth's gravity, chemical propulsion is genuinely impressive. The energy density of liquid hydrogen and liquid oxygen is extraordinary by any measure that mattered to engineers in the 20th century. But the solar system does not care about what impressed engineers in the 20th century. The distances are simply too large, and chemical rockets reach their limits fast. The The core problem is that a chemical rocket can only burn for minutes. It fires, it accelerates, and then it coasts. Everything after the burn is free fall, the spacecraft falling along a curve dictated by gravity, unable to speed up further unless it fires again. And firing again means carrying more fuel, which means the rocket has to be larger to lift that fuel, which means you need still more fuel to lift the larger rocket. Engineers call this the tyranny of the rocket equation. Every kilogram of fuel you add to a spacecraft costs you more fuel to carry it. The math punishes you for ambition. This is why Hohmann transfers are the dominant strategy. Not because they are fast, but because they minimize the fuel required to get anywhere at all. Chemical propulsion optimized for efficiency, rather than speed, is the only version of chemical propulsion that works across interplanetary distances. Ion propulsion breaks that logic. Instead of burning a chemical fuel, an ion engine takes a propellant, usually xenon gas, and ionizes it, stripping electrons away to create charged particles, then accelerates those particles through an electric field and ejects them at speeds roughly 10 times higher than a chemical exhaust plume. The thrust produced is tiny. At full power, the Dawn spacecraft's ion engines generated about 90 millinewtons of force, roughly the weight of a small sheet of paper resting on your hand. That is not a misprint, but because the exhaust velocity is so much higher, the engine extracts far more useful work from every kilogram of propellant. And because the thrust never stops, the spacecraft keeps accelerating. Over weeks, the small push adds up. Over months, a spacecraft on ion propulsion can reach speeds that would have required enormous fuel loads from a chemical system. Dawn used 3 ion engines to orbit Vesta in 2011, then break out of that orbit and travel to Ceres, arriving in 2015. No chemical rocket mission could have done both. The flexibility was the point. Ion propulsion can redirect a spacecraft in ways that chemical systems cannot afford. The limitation is that ion engines require electrical power to run, which means large solar panels or a nuclear power source, and the thrust is too gentle to escape a planet's gravity well on its own. Ion propulsion is a deep space technology, not a launch technology. But for the cruise phase of long missions, the years of travel between planets, it changes what is achievable. A Mars mission using advanced ion propulsion could potentially cut transit times to 3 or 4 months. That alone would transform the calculus for crewed missions. Nuclear thermal propulsion pushes further. The concept was seriously developed in the United States under a program called NERVA, Nuclear Engine for Rocket Vehicle Application, which ran from the late 1950s through 1972. The idea is to use a nuclear reactor to heat a propellant, usually hydrogen, to extremely high temperatures, then eject it through a nozzle. No combustion, just heat. Because the exhaust temperatures achievable with a reactor are roughly twice what chemical combustion can reach, the exhaust velocity doubles, and the efficiency roughly doubles with it. Engineers project that a nuclear thermal rocket could cut a Mars transit from 8 months to somewhere around 4. The program was cancelled in 1972 as NASA's budget collapsed after Apollo. The technology worked. The engines were tested on the ground. They were never flown. Nuclear pulse propulsion is something else entirely. Project Orion, studied seriously in the late 1950s and early 1960s, proposed a spacecraft that would detonate a series of small nuclear charges behind a massive pusher plate, absorbing each shock through a system of hydraulic dampeners and converting the blast into forward momentum. The numbers were startling. An Orion vehicle could potentially reach Mars in weeks rather than months, and some designs suggested transit times to the outer planets measured in months rather than decades. Freeman Dyson, one of the physicists involved, described it as the most capable large spacecraft ever seriously designed. It was never built. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, effectively ended it. The physics was sound. The politics were not. Solar sails operate on a completely different principle, using the pressure of sunlight itself as a propellant-free source of thrust. Photons carry momentum, and when they reflect off a large, thin surface, they transfer that momentum to the sail. JAXA's Icarus mission, launched in 2010, demonstrated the technology in deep space, unfurling a 14-meter sail and confirming measurable photon-driven acceleration. The thrust is even smaller than an ion engine and falls off as the spacecraft moves away from the Sun. A solar sail heading toward the outer planets becomes less effective the farther it travels. Toward the inner solar system, toward Mercury or Venus, solar sails become more interesting. But for reaching Jupiter or Saturn in any reduced time frame, sunlight is too faint to do meaningful work. The most radical concept currently under discussion is laser propulsion. The Breakthrough Starshot initiative has proposed accelerating extremely small, lightweight probes, chip-scale instruments attached to gossamer sails, using a ground-based laser array powerful enough to push them to 20% of the speed of light. At that velocity, such a probe could reach the nearest star in roughly 20 years. The same principle applied within the solar system would reduce travel times to outer planets from years to hours. But the probes would be microscopic. No scientific instrument of any complexity could survive the acceleration. No crude vehicle comes anywhere close to being compatible with the concept. The technology required for the ground-based laser array does not yet exist at the necessary scale. Breakthrough Starshot is a serious research program, but its practical applications to planetary exploration remain entirely theoretical. What is actually flying today, on real missions, is chemical propulsion and ion propulsion. Nuclear thermal has never left the ground. Nuclear pulse was never built. Solar sails have demonstrated thrust but not planetary missions. Laser propulsion exists on paper. The gap between what is theoretically possible and what is operationally available is measured in decades of engineering, funding, and political will. Until one of those technologies makes it off a drawing board and onto a launch pad, the answer to how long it takes to reach any planet will continue to be measured not in weeks, but in years. If you tried to plan a mission to every planet in the solar system, one after another from closest to furthest, the total time that comes back is not comfortable. Start with Mercury, the closest planet to the Sun, the one that looks like the obvious first stop. A direct flyby, the kind Mariner 10 managed in 1973, takes roughly 147 days. But a flyby gives you hours of useful data. If you want real science, you need orbit. MESSENGER needed 7 years. BepiColombo needed 8. The reason is the gravity well. Mercury sits deep inside the Sun's pull, moving fast, and to match its speed you have to shed an enormous amount of energy through a chain of planetary flybys before you can even attempt orbital insertion. So the first planet alone, if you are doing it properly, consumes the better part of a decade before you are ready to move on. Venus is next. The transit time, measured cleanly, runs between 100 and 150 days. That part is fast, but Venus is not just a destination. It is a tool, a gravitational waypoint that spacecraft have been borrowing from for 50 years. Cassini swung past Venus twice before heading towards Saturn. Parker's solar probe used it 7 times. The question of how long Venus takes depends entirely on what you are using it for and where you need to go next. If you are continuing outward through the solar system, you may find that Venus is most valuable as a speed adjustment, and adjusting speed through gravity takes time. It takes months of carefully timed approach trajectories. It takes geometry that only lines up under specific conditions. Mars comes after that. The average Hohmann transfer runs about 259 days, just over 8 months. Perseverance covered it in roughly 7. That sounds manageable until you account for the launch window. Earth and Mars align for efficient transfers only once every 26 months. Miss that window by a week, and you wait more than 2 years for the planets to come back around. A mission building an itinerary across the entire solar system cannot simply leave Mars when it is finished. It has to leave when the orbital geometry permits, or the energy cost to continue becomes prohibitive. So Mars adds not just 8 months of transit, but potentially another year or more of waiting in place before the next leg becomes feasible. Then the scale shifts. Past the asteroid belt, the solar system stops operating on the timescales that feel like recognizable human planning. Jupiter sits more than 5 times as far from the Sun as Earth. The fastest missions reached it in about 18 months. Galileo, which actually entered orbit, took 6 years. Juno took 5. If the goal is a serious orbiting mission, the minimum realistic figure is somewhere in that 5 to 6 year range. A flyby shaves time, but a flyby gives you a few hours of data at closest approach, and then the planet is behind you and receding. The Voyager spacecraft were flybys, and they changed our understanding of the solar system permanently. But they answered certain questions while leaving others completely open. Saturn adds 7 more years. Cassini's trajectory, which remains the definitive example of how you reach Saturn with current propulsion technology, consumed 6 years and 9 months from launch to orbital insertion. That included 2 Venus flybys, 1 Earth flyby, and 1 Jupiter flyby. Each of those encounters had to hit its timing within seconds. Each one added months to the calendar. There is no shortcut available with chemical propulsion. The energy required to reach Saturn directly, without gravity assists, would demand a rocket beyond anything ever built. So you take the 7 years, you build in the planetary encounters, you accept that everyone who designed the spacecraft will be considerably older by the time it starts returning science. Uranus sits roughly twice as far from Earth as Saturn does. Voyager 2 reached it in 8.5 years after leaving Earth, but Voyager 2 was on a trajectory optimized by an extraordinarily rare planetary alignment. Current estimates for a dedicated Uranus orbiter, using the best gravity assist options available in the near future, land in the range of 13 to 15 years of transit time. There is no mission currently flying toward Uranus. There is no mission in approved development flying toward Uranus. The planet has had 1 visitor in the entire history of space exploration, and that visitor spent a matter of hours in its vicinity before continuing on. Neptune takes 12 years at minimum. Voyager 2 required exactly that. Launched in 1977, arriving in 1989, having used Jupiter, Saturn and Uranus as successive slingshots along the way. That planetary alignment that made Voyager 2's trajectory possible occurs once every 175 years. Outside of those rare windows, a mission to Neptune demands either a very long time or a very large rocket, and usually both. No orbiter has ever been sent. No lander has ever been proposed in any serious funded capacity. Neptune remains, in practical mission planning terms, almost unreachable with current technology on any timeline that fits within a single human career. Add those numbers together: Mercury, perhaps 8 years. Venus adds a few months to the baseline but reshapes every trajectory that follows. Mars adds 8 months of transit and potentially 2 years of waiting. Jupiter adds at minimum 5 years. Saturn adds 7. Uranus adds 13 to 15. Neptune adds 12. A sequential mission touching every planet as an orbiter, with realistic waiting periods at each destination, runs well past 60 years of total elapsed time. Even a stripped-down sequential flyby mission, no orbital insertion at any planet, designed purely for speed, passes each world once and moves on. That version, optimized aggressively, still takes more than 30 years to reach Neptune. The numbers are not going to improve meaningfully until the fundamental technology changes, and the technology has not changed in any essential way since Mariner 4 became the first spacecraft to reach Mars in 1965. The solar system looks small in the diagrams you find in textbooks. 8 planets arranged in a tidy row, everything labelled, distances implied but never felt. The planets sit there as coloured dots, a few inches apart, and your eye moves across the whole system in a second. What those diagrams cannot show you is that the gap between Earth and Neptune, rendered to actual scale, would leave most of the page blank. The planets would be invisible. There would be nothing to see but empty space. Every mission described in this video required engineers and scientists to spend years of their working lives staring at that emptiness. They sent a spacecraft across it and then waited for signals traveling at the speed of light to make the crossing, minutes for the inner planets, hours for the outer ones. If something went wrong, the spacecraft was already dead before any response could arrive. The teams on the ground knew this. They built their machines to survive alone, to make decisions without them, and then they let go. The human dimension of this is worth sitting with. The engineers who designed Cassini in the mid-1980s were, in some cases, retired by the time it entered Saturn orbit in 2004. They spent careers on a single machine and watched it succeed from a distance measured in years. The scientists who built Voyager 2 were young researchers in the early 1970s. They were middle-aged when it reached Neptune in 1989. Some of them did not live to see it cross into interstellar space in 2018, still transmitting, still moving outward. The distances are not abstract numbers in a table. They are a measure of how much human time it costs to cross them. Careers, decades, in some cases, entire lives. None of that has changed. The same orbital mechanics that governed Mariner 10 govern BepiColombo today. The same vast stretches of nothing that Voyager crossed are still out there, unchanged, indifferent to how much faster our computers have become. The planets are still out there, still moving on their orbits, still separated from us by distances that defeat any intuitive sense of scale, and the fact that we have reached all of them, even briefly, even once, remains one of the stranger things humanity has ever managed to do.